Welcome back to the lecture series on design for biosecurity. And the fag end of the last week, we talked about the whole cell biosensor, and I shared with you the basic concept of the whole cell biosensors, which is somewhere in between the estimation what we do from bodily fluid, in vitro estimation from blood, urine, sweat, versus the in vivo measurements where we use wide array of spectroscopic, optical, acoustics, electrochemical techniques. Somewhere in between lies the world of whole cell biosensors. And I shared with you the resting membrane potential, where I go run you through the slides. It is somewhere here, where I told you that most of the cells, so the body could be classified into the world of excitable cells and non-excitable cells. So we are not dealing with non-excitable cells at this point. We are only dealing with the excitable cells, and the excitable cells are called excitability because they generate electrical impulse. And based on that, the different excitable cells what we discussed about are all the neurons, both central nervous system neuron and peripheral nervous system neurons. Then we talk about the cardiac myocytes. So basically all the cardiac cells could be divided into two different kind of excitable cell: cardiac myocytes, which largely compose the heart, and cardiac pacemaker, which is only 2 to 3% of the total cardiac cells. They set the tone of the heart. And third one is the neuroendocrine cells. So these are the three key family of electrically excitable cells. Then I talked to you about the resting membrane potential, where you place an electrode inside the cell and one outside the cell, and you try to measure the potential difference across them, and then you observe that most of the cells lies in -70 to -80 and sometime even -90 millivolt. And that's where we talked about when you plot it, you see something like this. Yet I also highlighted there are cells which will show you something like this, and it is happening spontaneously, right? This is up to this we went. Now the question where I left the last class was, of course, there is one more point I discussed, is why inside the cell there is less sodium versus outside, because we all believe that life has evolved from the seawater. Of course, that opens up a curious question, why seawater is so saline. There are theories for it, but this is not the purview of this class, so I will not discuss that. But these are some of the interesting things of nature, why ocean water is so saline. So now, assuming the life has evolved from there, so life has to develop a chamber which will not have that much sodium, and that's how possibly the cell has arrived. What I told you about this wonderful thing, Nernst equation. This Nernst equation will tell you why the membrane potential is at this level. We are not taking this special case of the spontaneous activity of the pacemaker cell at this point. I will come to this in a couple of classes. I will come to this, why it is and what determines. So this is our experimental observation. The cells are sitting at -70, -80, or -90 millivolt. Why is it so? How you could theoretically explain this situation? So this thing can be explained by a celebrated equation or a celebrated work of Walter Nernst. Who was Walter Nernst? Walter Nernst was a physical chemist, physicist, you can call it chemist, whichever you want to call him. But above all, a seeker for truth. And much of his legendary work, what we today know as Nernst equation, evolved at the in the backdrop when the whole world was celebrating the evolving or the starting era of quantum mechanics. It was the time when some of the celebrated people like Schrodinger, de Broglie, Einstein, and Max Planck, and series of other quantum physicists, Heisenberg, they are all busy talking about the dual nature of light, means particle nature and the wave nature, and things are found in quanta or in packets of particles, while the whole scientific genre you can call of that time, 1910, 1920, 1930, they're all busy from classical mechanics to discovering the next breakthrough, which is the quantum mechanics. In that era, Walter Nernst was working on a very different problem, entirely different from the rest. He was a very well respected man, the German, and he was working on a problem which I will just narrate you, and that will help you to understand, and that has a direct link to understand why membrane potential is -8. So, think of a generic situation. Forget about we are talking about cell or anything, but think of a situation like this. Say for example, here you have a confined space. Okay, confined space has two different kind of. Let's just start a simplest, or let's just start with the simplest of all. Say for example, you have particles of A's outside and you have particles of inside. So, obviously, as you could see from inside versus outside, this is all outside, there are only 4 A's out here and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, there are 12 A's outside and there are 4 A's outside, and if given an opportunity for them to equilibrate, a chemical equilibration, what will happen? So, if we by sheer common sense, this is at higher potential outside, so they will try to come here, so that they balance each other. So, the balancing will happen 12 plus 4 making it 16, 16 divided by 2 makes it 8. So, automatically in order to balance it, 8 of these ones, okay. So, there are 12 out here. So, each side will be 8. So, 4 of these ones, once they will get inside this confined space, it will balance itself. This is with the assumption that the mobility of A is free without any inhibition. Fair enough? Understood? Remember this point. Now, in this situation, I add one more parameter. Okay. I add a parameter, say I say that A has a charge. See, all A's are positively charged. So, now not only the concentration has to be balanced. So, first what we balanced is concentration, right? Now, so what we did is concentration balance. Next, if there are charges, so the charges has to be balanced, right? So, automatically once there will be 8 A's inside and 8 A's outside. So, there will be 8 positive charge inside, 8 negative charge inside, 8 A's inside, 8 A's outside. Very simple situation. Good. We can solve this. Now, I increase the complexity of this problem in the next level. So, the complexity is this. I introduce another molecule. Say for example, instead of A, I introduce another particle, say B. and I say there is this B which has negative charge, and there are some B's outside which has negative charge. Fair enough. So, let us count how many B's are there. You have 1, 2, 3, 4, 5, 6, 7. So, there are altogether 7 B's outside. Fair enough. And let us see how many B's are inside. 1, 2, 3, 4. Fine. So, there are 4 B's inside. So, 7 plus 4, 11. Now, again if the condition is same, that the A's and B's can balance each other, what will happen is that A's are moving, A will balance themselves and B's will also balance themselves. So, 7 plus 4, 11. So, 5, 5 and 1 B will keep moving back and forth. Accepted up to this point, because there are 7 B's plus 4 B's, 11, 5 plus 5. So, 5 inside. So, 1 B gets in. So, it makes it 5, this makes it 6, but still there is imbalance, but 1 B can move back and forth. Now, up to this it is all simple, right. So, you have balanced the charges of A and charges, you have balanced B, but B is a negative charge. Problem arises. Now, here is the problem. Problem is, suppose I say that B can only enter, cannot come out, or these B's or B's cannot go out of the cell, but B's can enter inside the room. Now, what? How you are going to balance it through? You understand the situation. So, that means if B's can enter inside, then what will happen? There are 1, 2, 3, 4, 5, 6, 7. These 7 B's can directly enter inside the cell. If 7 B's enter inside the cell, there are already 4. 7 plus 4, it becomes 11, right. Now, if they enter, they cannot balance. So, it means the charge balance will be in a question as well as the concentration balance. Now, you are realizing the complexity of the situation. If as long as there is a free mobility of both the ions, you are good to go, no problem. You can do a charge balance, you can do a mass balance or a concentration balance, whatsoever way you want to do it. But how are you going to do this? Now, here there is a restriction on the flow of a component, right. Now, think of the situation. That brings us to a very interesting situation. Now, if you break this problem in a simple Nernst era problem, it was basically to say for example, here you have a membrane, and this membrane is a semi-permeable membrane. Okay. So, this is the left hand side and this is right hand side. Okay. RHS, LHS. Fair enough. And this membrane is semi-permeable. Done. And on this side you have lot of A's, as usual what I said, and here you have few A's, and of course, if they are semi permeable and we allow both A's can move both sides. So, when I indicate A, I said A can move both sides, and you have B which can only move from right hand side to left hand side. Okay, just the arrow shows from right hand side to left hand side, and there are B's here. Right. Now, A's will balance themselves because they can move both sides. So, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Let us increase one more A to make it simple. 4 A's and 6 A's on this side. So, automatically there will be 6, and 2 A's can go to that side, and make it 1, 2, 3, 4, 5, 6 and 1, 2, 3, 4, 5, 6. So, 1A could go to that side and make it 5 and their A's are balanced. Now, for B there is a problem. On this side it is higher gradient. There are altogether 1, 2, 3, 4, 5 and B's can move from right hand side to left hand side. Now, in order to balance it, 1B moves here, it's 3 and 3. Up to this it is fine, B can balance. But now the problem can become complex. How problem can become complex? If I introduce charge into them. So, for example, what I was trying to explain to you. Now, the problem can become extremely challenging. Then, so 1B moves here, so it carries a charge. Now, say for example, I make it slightly more complex. It has another particle C and P, and both has negative charge in them. So, there are 3 C's which has negative charge. So, if you look at from the charge perspective, now let us count the charges. How many charges are there? 1 negative, 2 negative, 3 negative, 4 negative, 5 negative. So, there are 5 negative charges on this side and there are 1, 2, 3, 4, 5, 6 positive charges. Fair enough? 1, 2, 3, 4, 5, 6, 7. Sorry. So, there are, assuming this B is on this side. So, there are not 5, there are 7 negative charges on this side. On the other hand, on this side, you have, so let us assume this has already moved there. So, so there is negative charges are 1, 2, 3, 4. So, 4 negative charges and 1, 2, 3, 4 positive charges. Now, look at this. Here is a situation. There are 7 negative charges and there are 4 negative charges. By the charge balance, it should be around 11. So, 5, 5, 1 is moving back and forth, but that can only happen provided all the molecules can move. But we set a condition that P, C, 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 they cannot cross to the other side. It is a semi-permeable membrane. They will be confined only to this side. That means 1, 2, 3, 4, 5. 5 charges cannot move. So, it will always have 5 negative all the time without any biasness, right. Now, there are 2 B's, they cannot move to that side because B can only travel from left to right. So, that means there will be always 7 negative charges in this situation. How this guy could balance it? This is already a less than negative charges. So, some negative charges should move to this side, but none can move. But then how you determine on this situation, what will be the potential drop? And that exactly is the problem of the cell. When we talk about a cell, we observed it sitting at minus 80 millivolt. Minus 80 millivolt, when we are talking about, if you look back, let us talk about this part. It is sitting at minus, and we have to explain why it is minus 80 millivolt, right. Now, this was the problem of figuring out what will be the voltage across this membrane, and that is where came the most celebrated equation of Walton-Nernst, which says E is the voltage cross at minus 60 log. This is all simplified version of it, I am telling you. This value 60 is coming from natural log RTL, and I have converted all that for your simplicity. E is in millivolt. Now, what does this mean? So, this is that celebrated Nernst equation for which Walton-Nernst was awarded the Nobel Prize. what does this say? This say, now let's get back to the cellular equation. Here you have a cell, okay, lipid bilayer with protein structures, something like this, right? And this is outside, and this is inside. Inside you have a nucleus which has DNA. You have a lot of organelles like mitochondria. If it is a, this is nucleus, this is mitochondria, this is Golgi body. If it is a plant cell, it will have chloroplast, endoplasmic reticulum, ER, then you have SR, sarcoplasmic reticulum, so on and so forth. There are a series of them. Now, I have already mentioned that if you poke an electrode here versus an electrode outside, the voltage across is minus 90 millivolt. This we have already discussed. And now what we are trying to discuss is why it is minus 90 millivolt. Now, there are certain very interesting features, what we will be talking in the next class about who can move and who cannot move and how that could be reached. So, I'll close in here, and next class will continue with the Nernst equation a little bit, and then we will move on to the measurement techniques. Thank you.